Good morning, everybody. I cannot see you all because limitations of my screen. I will talk about this with God later on today because I got an idea. Welcome to the course. Let me start by telling you that this is a very tough course, and you are lucky because we have 2 days this week and 3 days next week. Sometimes I also run this course within 1 week, so then you have no time to recover from all the stories. We have sessions of about 3 hours every morning of the course, and in addition to that, there will be homework for about an hour in between the sessions. And as you can see, we will discuss, and the homework will be running exercises, because basically the only way how I can learn you how to look at spectra is by having you to do it yourself. And that's what we are going to do in these exercises. And each morning we will start, of course not today, but each morning we will start by discussing the exercises which you did in between the 2 sessions. And that we will do in a very interactive way. So I actually hope that one of you will, for each exercise, present some answers and so on and so forth. And that will do. And sometimes I will do a certain exercise because I have specific reasons for doing so. And you can listen in and see what's going on. So I try to get the course as interactive as possible, which means that you can interrupt me for questions and discussion at any time. And I will hope to be able to see this going. You can use your microphone or do it in any other way. I'm like a diesel train, so I continue. And if you don't ask, I simply assume that everything is clear. And when it's not, you have to interfere. That's basically the story. So each of the morning sessions takes about 3 hours, and every hour we have a 10 minutes break, and that will be around the full hour, but also depends on how we are in the series of presentations. With respect to the exercises, they are in the manual which you got in an electronic form. You also received a separate file where all the exercises are together, because I think it might be useful to actually print the exercise file, because it's much easier to work on them. And that's why I made this separate file. And that's basically the idea. If you would have any questions which you don't want to ask in public, but ask to me personally, this is the email address which you can use, and you can do whatever you do, and you will get a reply. So that's basically the idea. I think I would like to make a small round so everybody knows who is on the course. And basically, I would like to tell you who you are, where do you work, and just in short notice, the type of work you do, the type of molecules you work on, and so on and so forth. Yeah? Can we do that in that way? And I will do it in a alphabetic order, I think. So I first ask Adam to, that's my alphabetic order, which is the
sorry, Adam has some technical issues at the moment, so if you can go back to him at the end.
Okay, he has some, okay. Then we go to Albert. Is Albert there? Yeah, he is there.
Good morning. Can you hear me?
I can see you, yes. And I can hear you, which is even more important.
So my name is Albert. I'm currently working in targeted metabolomics unit at the Weizmann Institute of Science. And mostly what we are doing is targeted analysis using LCMS analysis.
I can see you, but hearing what you say is a bit difficult, I think, for most of us. So speak up a little bit more, closer to the microphone, perhaps.
Okay, I'll try.
I see that you are at work,
now?
so you are obliged to have the mouth cap.
Yes. So I work in the targeted metabolomics unit at the Weizmann Institute of Science. Mostly we do targeted analysis of small molecules using LCMS and LC.
Okay, thank you. Then we go to Alexei. He was there.
Hi, you hear me? I'm from Weizmann Institute, metabolomic profile units, and I'm dealing with mass spectra as well.
Okay, thank you. And then we go to Anna. You have to switch on the microphone, please. Unmute. Okay.
Hello, I'm Anna. I'm from Technion, from cancer and cannabinoids laboratory of Professor Daly Mary, and I work with the GCMS and detected and terpenes.
Okay. Okay. Then we go to Twill.
You can go back to Adam, by the way. I think he's with us, if you want to.
Yeah, that's okay. That's okay. Then we go to Adam.
Good morning.
Ah, there you are.
He will speak through me. Sorry, we are a few people sitting with each one with our laptop.
Okay.
Hello, good morning. I'm from Weizmann Institute of Science, and I work with LCMS and GCMS, and I mostly identify plant metabolites. That's it.
Okay, thank you.
My turn?
Yeah, okay, great.
Hi, I'm Dvir. I'm from Ben-Gurion University, and I'm using LCMS also on plant research, and I do untargeted approach at Yariv Brutman's laboratory.
Okay. Then we go to Guy.
Guy, if you can hear us, please open your microphone. If not, you can write in the chat and I'll read it out loud.
Yeah.
Yeah.
Oh.
Do you hear me now?
Great. Yeah.
Hi, sorry for not seeing me. I don't have a camera. I'm from Weizmann Institute, and I'm from the non-targeted metabolomics unit.
Okay. Then we go to Ilana. Is she there?
Actually, I don't see her, so skip on and I'll try to call
We
her.
go to Irina.
Hi, I'm Irina. Do you hear me?
Yes, we hear you. I can't see
Sorry,
you, but I hear you.
Sorry, I don't have a camera.
Okay, no problem.
I'm from Weizmann Institute, from Metabolic Profiling Unit, and I also work with the LCMS.
Okay. Then we go to Jonathan.
Hello, you hear me?
Yes, I hear you.
Yes, Jonathan Gorelick from the Eastern Regional R&D Center, affiliated with the Ministry of Science and Ariel University, working on plant secondary metabolites, so quantification, identification, quantification with LCMS, GCMS, etc.
Okay, thank you. Then we go to Leah. Is she there?
No, again, I can't see her right now.
Then we have Maxim.
Hello, I'm Maxim from Metabolic Profiling Unit, Weizmann Institute of Science. And I work with high mobility mass specs mostly. Had some experience with identifying molecules from fragments.
Okay, thank you. Then we have Neil. I saw
Hi
him.
everybody, I'm also from the Weizmann Institute. I'm from the group of Asaf Aaroni, the Plant Sciences Department. We do mainly untargeted analysis using LCMS. I'm a computational guy, so I'm working methodologically, not in any specific type of compounds, but mainly computational processing and statistical analysis.
Okay, okay. And then we have Paula or Shirley. What should I call you?
Shirley, it's good. It's fine.
Okay.
So I'm a postdoc also at Professor Asaf Aaroni's lab, working also with LCMS on small molecules from plants.
Okay, thank you. Then we have Shimon.
I'm Shimon from Ben-Gurion University. We work on the evolution of central metabolism of bacteria using LCMS and GCMS.
Okay. And then we have Sergey.
Okay, I'm working at Weizmann Institute in the Metabolic Profiling Unit, and we are using for our job high resolution mass specs and GCMS and so on.
Okay. And we have Veronica.
Hi, I'm Veronica. I'm a postdoc since 1 month, but previously and still now I work with Dr. Shimon and Dr. Yariv. And I work with GCMS and LCMS, mostly in bacteria, but I also do some collaborations in human cells and saliva of insects.
Okay, okay. And we have Yariv.
Hi, my name is Yariv. I'm from Ben-Gurion University, and we work mostly on plants, and we work on with LCMS, a bit GCMS, mainly secondary metabolites in plants and lipids profiling.
Okay. And then finally we have Sophia. From my own country.
Yes,
Or
I'm
more or less.
Hungarian, but
Yeah,
yes, I work in the Netherlands about healthcare products, and I use LCMS to identify unknown impurities in pharmaceutical products.
Okay, thank you.
And
Thank you
Tom
all.
wanted me to say hi to you.
Yeah, thank you. Say hi to him back for me. Okay, it's funny to hear so many people working on plant metabolites, and perhaps I should tell you that some I think 8 years ago or so, I actually started to develop a course, especially on these type of biomolecules, so plant metabolites, lipids, and so on and so forth. But in the end, I never finished the course. And so it was under development for some time, and it would be very useful for most of you. But we will simply do the course as I have done it before with Bioforum in July, and you will learn from it, because there's still a lot of information also for you with respect to the things which you see. And of course, there will be some sessions, for instance, when we discuss about chlorinated or halogenated compounds, you will not see them in your samples, but they can still be useful to know what is going on. So basically, today we look at mass spectra, and as of Wednesday, we will actually start looking at MSMS spectra. So that's the general idea, and the program as it is there. And I can tell you next Monday will be the toughest day, because then we have most of the material, but all other days will be tough as well. But the last 2 days will be a bit more relaxing, perhaps. Okay, that's there for you to know. I have some competition in these type of interpretation courses, especially in the US. And at a certain point, I looked at one of the programs of these courses, and what I saw is that what they do is they start by, they have a 2-day course, and they start in the morning by explaining what is electrospray. And then after coffee, they explain all the instruments and how it works and what is going on and so on and so forth. And then after lunch, they start discussing about mass spectra. Well, I will do it a little bit different. So basically, what I say is we have 2 types of instruments. We have instruments which provide us with unit mass resolutions, like quadrupoles, tandem quadrupoles, ion traps, and we have high resolution instruments, which allow us to do accurate M/Z, which means that the error in measuring the mass for small molecules is in the 3rd decimal place. Yeah, these are the time of flight and the orbit trap instruments. And I have seen most of you have access to these type of instruments. So that's about instruments. Let's talk about ionization. Basically, we have 2 major groups of ionization techniques, which are the hard ionization and the soft ionization. The hard ionization is the electron ionization which you use in GCMS. The soft ionization is electrospray, is APCI, is matrix-assisted laser desorption ionization, and a whole lot of other technologies. And the major difference between the hard ionization and the soft ionization is in the type of ions which are generated. And you could say the difference between the 2 is just an electron, but it makes all the difference. So if we do electron ionization in GCMS, we have interaction between high energy electrons and our analyte molecules. And when I say high energy electrons, I mean 70 electron volt electrons. And 70 electron volt is about 4,000 kilojoule per mole. While the bond strength in a molecule is around 300 kilojoule per mole. So it's really high energy. In the interaction between the high energy electrons and our analyte molecule, what we see is the electron kicks out an electron from a molecule. And to me, all molecules have an even number of electrons. If a molecule doesn't have an even number of electrons, I don't call it a molecule, I call it a radical, just to make the differentiation. So when you kick out an electron out of a molecule, you get a positive charge with an odd number of electrons. So what we create is what is called the molecular ion, which by definition is an odd electron ion. And I use this term quite a lot. And in this interaction, a lot of energy is transferred to the molecular ion, resulting in in-source fragmentation. And that's what we see in GCMS. Yeah. And later on, we will actually have a look at the type of fragmentation we get in EI and see whether we can learn something from that. Yes, we can, with respect to what we do in LCMS. Well, in LCMS, we don't use electron ionization, we use electrospray or APCI. Yeah. And in electrospray, we basically convert our analyte molecule into a protonated or deprotonated molecule. By adding or subtracting a proton from our molecule, we don't change the number of electrons. So we produce even electron ions. And some people say the M plus H is a molecular ion. That's wrong because it's not an odd electron ion. Some people call it the protonated molecular ion. Well, if you can protonate the molecular ion, you better find a very useful application for that, because I guess you will be asked to come to Stockholm in the beginning of December one year. I don't know when, but it might happen. So actually, the correct name for the M+H is the protonated molecule, or the deprotonated molecule for the M-H. And I can't think of any better name to explain what is there, because that's what we do. In this interaction, we have low internal energy, so we don't see fragmentation. And that's the reason why we need to do MSMS in order to get structural information. The key point of this page is the difference between the odd electron ion and the even electron ion. Yeah, and basically you can say the difference is just 1 electron, but it makes a lot of difference. So this difference is also on the basis of the 2 ways of expressing the nitrogen rule. The nitrogen rule tells you that if you have a molecule with an even molecular mass, you must have 0 or an even number of nitrogens in your molecule. And you should be aware of the fact that the nitrogen rule, to me, is the most important rule we have in mass spectrometry. I use it all the time. So basically, if you don't are familiar yet with the nitrogen rule, I will train you to get used to it. So if we have an odd molecular mass, we must have an odd number of nitrogens. This not only applies to a molecule, but also to a molecular ion or any other odd electron ion. If instead of producing a molecular ion, we produce a protonated molecule, we basically add, for a deprotonated molecule, subtract 1, which means that the nitrogen rule reverses. So if you have an even M/Z for a protonated molecule, you must have an odd number of nitrogens. And if you have an odd M/Z for the protonated molecule, you must have 0 or an even number of nitrogens. I always remember the nitrogen rule because at a certain stage, all the odds and evens go mixing up in your mind by using the ammonium ion, NH4+, which obviously is protonated ammonia. So it's an even electron ion with an M/Z of 18, which fits to the nitrogen rule. You should be aware of the fact that the basis for the nitrogen rule is actually a mathematical one, as I will show you shortly. I'll come back to that. Yeah. So what we measure with the mass spectrometer, and in that the mass spectrometer is unique, we measure mass. And the mass can be expressed in different way. Chemists use molecular weight. We as mass spectrometrists, at least for small molecules, use molecular mass, which is a monoisotopic mass based on the atomic mass of the most abundant naturally occurring isotope of an element present in a compound. Because most of the elements present in organic compounds occur in nature with more than one stable isotope. And I'm not referring to the radioactive isotopes like the tritium, the 3H isotope, or the 14C isotope. These are radioactive. No, these are stable isotopes I'm referring to. Yeah. And we use this definition for molecular mass. The monoisotopic mass as such can be expressed as a nominal value or an exact value based on the table, nominal values, exact values. And of course, if you would do everything correctly, you should always use exact mass. For all the exercises we do, we can actually use nominal values. The reason for that is, if we would use exact mass, the exercise would be an exercise in calculation skills rather than in chemistry. And I want you to be in the chemistry. But we will invoke exact mass every now and then. Yeah. The difference between the exact mass and the nominal mass is what we call in mass spectrometry the mass defect. And the mass defect in mass spectrometry is different from the mass defect in physics, which I'll come back to a little bit later. It's not important for us. We have this mass defect. And if you have a look at the table, you can see that there are, and you should be aware of the fact that since 1964 or so, the table is based on 1/12 of the carbon-12 isotope. So that's why carbon-12 is 12.0000. If you would have a table from 1960 or before, you would actually see the definition is different, because in those days it was oxygen, which was the counting point. So in the old tables, oxygen was 16.0000, but we have changed that at a certain point. Yeah, you can actually see that there are two elements, that is hydrogen and nitrogen, which have a positive mass defect, while all other elements have a negative mass defect. Because of the frequency of occurrence of hydrogen, most compounds in nature have a positive mass defect. So the exact mass is higher than the negative mass. And of course, we use the mass defect in high resolution mass spectrometry to do what we need to do there. You should also be aware of the subtle difference between the exact M/Z of an ion and the accurate M/Z of an ion. So the exact M/Z is the calculated, the theoretical value. The accurate M/Z is the measured value. And such a subtle difference is very difficult for US people. So from US companies, you can actually buy mass spectrometers which give you exact M/Z. Well, I only have one tool which can do exact M/Z, and that's my calculator. Yeah, you should also be aware of the fact that some mass calculation softwares ignore the mass of the electron. So if you would use with the old Waters MassLink software, you will actually do mass spectrometry as a science of what is impossible, because basically if you ignore the electron mass, you just work on neutrals. Yeah, I was saying there's a mathematical reason for the nitrogen rule, and I can illustrate it with this table, because in this table we have three types of elements. We have elements which have an odd mass and an odd valency, like hydrogen, fluorine, sodium, phosphor, chlorine, bromine, and iodine. We have elements which have an even mass and an even valency, which is true for carbon, for oxygen, for silicon, for sulfur. And then there's one element left, which is nitrogen, which has an odd valency and an even mass. So that's the mathematical basis for the nitrogen rule. So there's nothing magic there. It's just mathematics. And that's why it's always valid. That's the power of the nitrogen rule. I was referring to mass defects, and it's interesting to see what is going on with mass defects. So let's see and take a simple molecule like hexane, which has a mass defect of 0.1. And if from the hexane molecule you step by step put in a double bond, that means you take off two hydrogens, you see the effect on the mass defect. The same you can see in the other table, where we say let's have a look at the pyridine, which has a certain mass defect. And then we will modify the pyridine by adding a nitrogen. Well, then we have to add a hydrogen as well. So the mass defect increases. Or we add an oxygen, a fluorine, a sulfur, a chlorine, a bromine, an iodine, and you see that the mass defect is going down. For the brominated and iodated pyridine, you actually have a negative mass defect. So this is what is going on with the mass defect. You can also consider the mass defect in relation to mass. So what I made is I made a small oligomer of a peptide with alanine, threonine, leucine. And this is the elemental composition. This is the mass. You can actually see the monoisotopic mass and the average mass. And if you combine these, so the mass gets larger, you can actually see that the mass defect is increasing with mass. So here you have a mass defect of almost 2 units. With the average mass, the difference is even larger. So for larger molecules, you expect larger mass defects. One of the things I'm doing all the time is also introducing various terms. And one of the terms I should introduce to you is the difference between isomers and isobars. And I have to introduce you to that because I must be sure that you are aware of this difference. Isomers are compounds with identical elemental composition. And because of that, they have identical nominal and exact mass, but differences in structure. So here are 3 isomers. Isomers may be discriminated by LC, perhaps by fragmentation, but not by mass spectrometry itself. You might need to use NMR for that. Isobars are compounds with identical nominal mass. So the 3 red ones, and we can take another one from the 3 at the top. So we have 4 isobars, which have different elemental composition. So they have different structure, they have different exact mass. So by high resolution mass spectrometry, we can actually discriminate between these compounds. And that's important for you to be aware, the difference between isomers and isobars. Okay. What I could have done is told you a story of about an hour about what is going on in electrospray. And my general story about the ionization mechanism of electrospray is we don't have a clue at all about what is going on. And of course, there are beautiful stories about how electrospray works. But each part of this story, for each part of this story, I have data to prove it's different. So I actually believe we don't have a clue about what is going on in electrospray. But fortunately, we have some prediction power whether we will see something or not. So we can, in positive ion mode, when we want to produce a protonated molecule, we will be pretty successful if the molecule contains a nitrogen. If it does not contain a nitrogen, it should have a carbonyl, C-double-O. If it does not have either a nitrogen or a carbonyl, it might not be that easy to ionize it in electrospray positive ion mode. In negative ion mode, the situation is easier because you have to, in order to produce a deprotonated molecule, have to take off a hydrogen. So you actually need to have a site in the molecule where you can take off a hydrogen. That is, you need to have an acidic function, so a carboxylic acid function, or sulfonate, sulfate, phosphate. But how often do you see that? Or a aromatic OH, a phenolic OH, which is also acidic. In addition, you can produce negative ions, deprotonated molecules, based on the amide immunol tautomerism for amides and a similar tautomerism for sulfonamides. So basically what we have is we have the equilibrium between two states, the amide form and the iminol form. And if you have the iminol form, you have the OH where the hydrogen is acidic. So from this we can produce negative ions. And you see negative ions for amides, especially when this nitrogen-carbon double bond is conjugated to a larger aromatic system. Okay, one of the things which we will do a lot during this course is look at spectra. Perhaps I should tell you an anecdote that some 8 years ago or so, I was invited to act as an opponent in a PhD ceremony. And I said, yes, I will do that. And about 5 days before the actual ceremony, I found out they didn't send me a thesis. So I contacted the supervisor and I received the thesis 1 day before the actual ceremony, which is a bit late for reading the complete thesis. So what I actually did is I was reading the thesis like a comic. So only looking at the figures, that is, only looking at the mass spectra. And that's what we are going to do in this course. I should tell you that the candidate at the PhD ceremony had a very difficult time with me because I see far more in the mass spectrum than she did. Well, let's look at the spectra. So these are spectra, MS spectra, of what I think is an ideal compound for structural elucidation. That is a compound which gives data both in positive and negative ion mode. So in positive ion mode, we see the M plus H. In negative ion mode, we see the M minus H. So based on this, we would say the mass of this compound will be 232. We have two additional points of evidence, which is the M plus H plus 22, the 255, which is the M plus sodium. And we have the M minus H plus 60 in this particular case, which is the acetate adduct of this compound. So from this, we can state that most likely the mass of this compound is 232. And you hear me say most likely, because I always say I don't sell certainty, I only sell probability. I'm a scientist. Seeing these type of adducts allows you to set up a table where you see these type of adducts. And basically the table is based compared to the mass. So the difference, as we have seen between the M plus sodium and the M plus H, is the difference between M plus 23 and M plus 1 is the 22 we saw on the spectrum here. That's what we see. You may note that in the table there's also the M plus lithium. Well, you will never see an M plus lithium unless you have added lithium to your mobile phase. But I need the mass of lithium because I will play with lithium every now and then. So I decided to put it in this table. You should also be aware of the fact that if you have the acetonitrile adduct, the methanol adduct, the ammonium adduct, the formate adduct, the acetate adduct, the trifluoroacetate adduct, you must have these compounds present in your sample or in your mobile phase. This is not true for the sodium adduct, the potassium adduct, or the chloride adduct, because these elements are always present already in your solvents. If you buy a bottle of HPLC solvent, you get 10-4, 10-5 molar of sodium for free. You don't have to pay any extra. And if you have a compound with affinity for sodium, you will see the sodium adduct. And that's basically what you can see. And the same holds for the potassium adduct and the chloride adduct. Okay, so unlike GCMS, you should be aware of the fact that in LCMS, there's not such a thing as the LCMS spectrum of a compound, because the LCMS spectrum of a compound depends on the mobile phase composition. and perhaps experimental conditions. Yeah, and this is illustrated here for simvastatin, which is a cholesterol synthesase inhibitor, which is given to people who have high cholesterol or which have a history in heart disease. And as you can see, there's no nitrogen in the molecule. And if we analyze it without ammonium acetate in the mobile phase, so acetonitrol, water, and some acid perhaps, we will see the sodium adduct and the potassium adduct. And if we start adding ammonium acetate, we will actually see the M plus H appearing. We see the M plus ammonia, and we see reduction of the abundance of the M plus sodium and M plus potassium. Yeah, so the spectrum depends on the elemental composition. You also see a beautiful illustration of the nitrogen rule, because we have one ion here, the 436, which has an even M over Z, whereas all the others have an odd M over Z. By producing the ammonium adduct, we actually introduce the nitrogen in the molecule. So we see the action of the nitrogen rule. Yeah. Okay. So let's look at the next spectrum. And my question would be to you, could the 487 be the protonated molecule of this compound? Any ideas at your side?
It has 3 nitrogens, so no.
You have some background noise, Adam?
Adam wanted to say that it has 3 nitrogens. So, so no.
So you say 1, 2, 3, no. Yeah, I agree. Since we have 3 nitrogens, we must have an even M over Z. And the 487 is an odd M over Z. So actually, given also the size of the molecule, most likely the 244 is the M plus H, because we see plus 22 plus 38 for the sodium adduct and the potassium adduct. The 487 is something which we sometimes see, which is called an adduct bound dimer. In this particular case, a proton bound dimer, a 2M plus H. And this is something which you see especially at high concentrations. And instead of the M plus H, you can see the 2M plus H, you can see the 2M plus ammonia or the 2M plus sodium, or perhaps you see them all. In negative ion mode, you can also see the 2M minus H minus. Yeah, and this is a strong function of concentration. So if this would not be the spectrum at high concentration of cytarabine, but of an unknown, one of the things which you can do is dilute the sample 10 times, shoot again, and then this will go down much faster than the other peaks. This is a good indication that most likely you have 2M plus H. Another trick, of course, which you can do is to MSMS on the 487. And in 99% of the cases, you will just get the 244 without any product ions in between. So you have to be aware of the fact that this is something which can take place. And especially if you have quantitative analysis over a broad range, you have to check whether you don't have these things in your data. I should also point out to you that I believe that in many cases where we say we have a sodium adduct, we actually do not have a sodium adduct, but we actually have a protonated sodium salt. Because there are lots of compounds with acidic functions which are analyzed in positive ion mode. And a beautiful example is given here, which basically tells the whole story. And the example is an extremely important molecule, which is called ATP, adenosine triphosphate, And why it's important? Because if we wouldn't have this molecule, we would all be dead. Because the ATP is the energy source in our body. Well, what we have is, we have a base here, which it can easily be protonated. And we have a series of acidic functions. So what we see in the positive ion mode, 508, 506 in negative ion mode, so 507 would be the molecular mass, 1, 2, 3, 4, 5 nitrogens, so that could be, because it should be odd molecular mass because of the 5 nitrogens. What we see next to the M plus H is the 530. And you say it's an M plus sodium. I say no, it's not an M plus sodium. It's actually a protonated monosodium salt. And I come to that conclusion by having a look at the 552. Because the 552 is not the M plus 2 sodium. Because the M plus 2 sodium would have a mass of 553. It will have 2 charges. So we actually see it at M over Z to 76.5. In fact, the 552 is a, in this particular case, most likely protonated disodium salt or a sodiated monosodium salt. And this is the way I write this. And that we actually see this hydrogen sodium exchange at the acidic functions in the ions is nicely demonstrated in negative ion mode. Because in negative ion mode, we see the M minus H. We see the M minus H plus 22. You cannot have a sodium adduct in negative ion mode. So you must have a sodium salt there as a deprotonated form. And also the disodium salt in the as a deprotonated molecule, which is the 550. Yeah, and of course you cannot have the 3 sodium salt because then you don't have negative charge anymore. Yeah, so this is a subtle difference which is there, and negative ions nicely show that this is something which is actually going on. Okay, we were also referring to record mass, and with the sodium adducts and the potassium adducts, you have to be aware of the fact that they have a significant negative mass effect. So if you would have a molecule which shows M plus H, M plus sodium, M plus potassium, and you look at accurate mass values, you actually see that the mass effect is going down because of the sodium and the potassium. And that can be very useful and very helpful in these type of things. Finally, you should be aware of the fact that any molecule with a mass over 500 and more than one protonatable or deprotonatable group in electrospray can show multiply charged ions. And the mass spectrometer is measuring not mass, but it's measuring M over Z. So this is an example of a small peptide called bradykinin, and it's containing a lot of basic amino acids. So actually what we see is we see the singly charged ion, the M plus H, the doubly charged ion, the M plus 2H2 plus, and the triply charged ion, the M plus 3H3 plus. And of course, we can calculate the M over Z values of the doubly and the triply charged ions. But I always say that's not important because the mass spectrometer is doing that for you. What is important is if you assume or know that a 530.8 is a doubly charged ion, how to derive the mass of the molecule? Well, you use these equations for this. And that's very useful and very a simple procedure to do so. And in our next session, we will actually see some tools how you can decide whether this must be a doubly charged ion. You should be aware of the fact that for any of the effects I showed you, so adduct formation, proton bound dimers or adduct bound dimers, and also multiply charged ions, the relative abundance of the various ions may vary with concentration and most likely will actually change with solvent composition. And this is something which you always have to be aware of when you do quantitative analysis. And I have a beautiful example where at a certain stage I was acting as an intermediate between a department within a pharmaceutical industry where they didn't have any MS experience and a CRO doing some work for the pharmaceutical industry. And they were looking at a certain molecule, and they found out by doing an infusion of the molecule in the mass spectrometer at the CRO, they found out that it's producing a strong a strong M+2H2+ doubly charged ion. So they actually developed a SRM transition for it based on the doubly charged ion. But the problem was not in the mass spectrometry, the problem was in the chromatography. So what they had to do is they had to play with the mobile phase composition. And in the end, they succeeded to get the separation of the three molecules which were there. And they reported back to us, well, we have succeeded in getting the separation, but unfortunately, the sensitivity in the mass spectrometry is very poor. And then I said to them, what I would like to see is the MS spectrum of the compound under LC conditions. And then they said, no, that's not important because we do SRM, so we don't have to deal with the MS spectrum at all. That's not important. Then I said, I want to see the MS spectrum under LC conditions. No, but I'm the boss. Show me the MS spectrum under LC conditions. And they measured the spectrum and they actually got what I expected, that under the LC conditions, the spectrum changed. Instead of having the M+2H2+ as being the major peak, they only had a very small M+2H2+, and they had a huge M+H. So check the spectrum under real conditions, because that's what is important. That's what's going on. And with this message, I ask you, no, I should state that everything I told you is completely clear because there were no questions. Unfortunately, I don't believe that. So let me urge you, if you have questions, stop me and ask. Any questions at this point? If not, I see you in 10 minutes.
Wait, just 1 minute. Adam wants to comment something.
Okay. So you are in one room sharing a computer, or at least a microphone.
No, only sharing the room.
Okay.
We all have computers, but we share in the end one.
Okay.
I wanted to comment. It's maybe not really relevant, but it's something that I saw, and I think it might be related to nitrogen rule. And you said that even M to Z ratio will be only for nitrogen containing molecules. But I saw, for example, molecules, biological molecules that has plenty carbons around 100 and then much more protons. And even though they don't have nitrogen, the M to Z will be also even.
I will take this question into the next session, and I'll come back to that.
Yeah, great, thank you.
Because it's not true, and I will show you.
Okay.
Yeah. Okay. See you in 10 minutes from now. We'll have a break. And what is important for the break? Get away from your computer. walk around, to exercise, take a coffee or tea, because you have to relax. Don't start answering emails. Relax, 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 and move around. See you in 10 minutes.
Please don't leave the sessions, only mute your camera and microphone. We'll see you in 10 minutes.
Okay, let's move to our second presentation of this morning, which is on isotopes. I don't know how fluent you are with the isotopes. Let's tell the story. And basically, I could tell this complete story by just one page, this page. I will use a few more because that's more convenient. What the table actually shows is that most elements occurring in nature have more than one naturally occurring stable isotope. And actually, the relative abundance of these isotopes is given in the table. And basically, what you can see is that if you have a carbon in your molecule, the carbon actually comes with about 1% probability that it's not a carbon 12, but a carbon 13. Yeah. And if you have the carbon 13, you have one mass higher. So let's see what's going on and how this work. And in order to do so, I will go through an example. But before doing that, you should be aware of the fact that the numbers given here, so for the relative abundance and for the average mass based on the relative abundance, are actually some official values, some standard values, which are given. But the actual ratio between, for instance, hydrogen 1 and hydrogen 2 is varying over the planet. And this is nicely illustrated by looking at the atomic weight of hydrogen over the continent of the United States of America, where you actually see that there is a huge difference between what the mass is up here and what is the mass here at Miami Beach. And these differences indicate that the ratio between the hydrogen 1 and hydrogen 2 occurring in nature is actually fluctuating. And this is something which we use, for instance, using the ratio between carbon 12 and carbon 13 for doing verification of food products. So if I buy a bottle of orange juice and it says this is produced in Israel, I will be able to check this by looking at the C12, C13 ratio to see whether it's actually coming from Israel or perhaps from Spain or from Brazil, because they have different ratios of that. This is not the type of things which you can do with your type of instruments. You should be aware of the fact you need special tools for that. It's also used in sports doping. For instance, if somebody has a high testosterone, we will actually look at the T12, T13 ratio to decide whether this is a naturally occurring high testosterone level or whether it's inflicted by using some synthetic testosterone. And in the latter case, of course, the person in question is in trouble. Yeah, this is something which you have to be aware of. So let's see what is going on with the isotopes. And the easiest way is simply predict the isotopic pattern of a simple molecule. So let's take the decane molecule, C10H22. It cannot be protonated, so we have to produce a molecular ion. And the molecular ion will have an M over Z of 142 because 10 times 12 plus 22 is 142. It contains carbon. So what we actually see, because we have 10 carbons, each coming with a 1.1 probability, that's carbon 13 rather than carbon 12, we will actually get a peak at M over Z 143, which is 10 times 1.1 is 11% probability. And if I say to you, you have 11% probability that you have one carbon 13 in, there will be a certain probability as well. You immediately understand that there will be 2 carbon 13s in. And you can calculate and show, sorry, I go the wrong way, that would be 0.56%. So this is how the isotopic pattern of the C10H22 looks like. It's simple, straightforward. So let's rebuild the molecule, put in some complication. So what we do is we replace one of the hydrogens by chlorine. Then the mass goes up 34 units to M over Z 176, and we still create the molecular ion. Yeah, we have still 10 carbons, so we get a peak at 177, which is 11%. We also have, because of the 11%, we have the M+2 peak at M over Z 178, which will be the 0.56%. But now we have to be aware of the fact that at the M+2 peak, we will also have the contribution due to the 37 chlorine isotope, which is about 33%. So that's what we get. We have a combination of the 0.56% from the 30C2 and the contribution of about 33% of the 37 chlorine. Are we finished now? No, we are not finished, because in the compound with 37 chlorine isotope, we still have 10 carbon atoms. So we will see a peak at M over Z 179 being the 12C9, 13C1, 37 chlorine, which will be about 1/3, 33% of the 11%. So it will be 3.7%. And at 180, we will see the 12C8, 13C2, 37 chlorine, which will be around 0.2. So the actual pattern will look like this. Yeah. And you should be aware of the fact that for the 178, so the M+2 peak, we actually have 2 compounds, 2 isotopomers, where we basically can say we have the 13C0, 37 chlorine, and the 13C2, 35 chlorine. And because of the mass defects, they have different masses, and they differ about 10 millidalton difference. So you would need to have a resolution of about 20,000 to be able to resolve these 2 peaks, and all instruments can give you that. So that's something which we can do. Yeah. Okay. So in order to play with isotopes, we basically classify all elements according to their isotopic composition. And we classify them in 4 groups. We have the A elements, which are elements which have 1 stable isotope, like fluorine, phosphor, iodine, nitrogen, sodium. We have the A+1, which have a stable isotope at 1 unit higher than the most abundant one, which is carbon and nitrogen. We have the A+2 elements, which have a stable isotope at 2 units higher. And if you go to the table, we can see that this is true for chlorine and bromine. And for sulfur, silicon, and oxygen, we have both an A+1 and an A+2 isotope. But since the A+2 isotope is more specific because of carbon, we count oxygen, silicon, and sulfur to the A+2 elements. And other A+2 elements are, for instance, silver and copper, to name a few which I saw in some spectra once. And then we have all other elements which do not fit to these, which have more complex isotope patterns. A good example is lithium, which shows an M-1 isotope peak of about 8%. And in the picture, you see the isotope pattern of tin. And when you see this and you want to play with isotopes, you shouldn't start working on a compound with tin, because that's quite complex. Isotope peaks contain information, both on known compounds and unknown compounds. And prediction of isotope patterns, we have software for that because they require complex calculations. And that's something which you have to be aware of. And we have these softwares so we can play with these. And since we know, we have seen how to do it, we can now do it. So we have the isotopic contributions here. I have another table with the same, basically the same information, but presented in a slightly different way. And some people like the first table, some people like the second table. You can keep them both. You don't have to send me one back from your manual. You can keep them both. Yeah. There are two pieces of information from the isotope pattern which are very easy to see. The first, the presence of chlorines and bromines, because they give rise to peaks 2 m/z units apart with high abundance. So in most cases, you will always immediately see from the isotope pattern, we must have a chlorine or a bromine present. And most of the compounds we have a number of chlorines, a number of chlorines, or a bit there. I once met a person from in one of my courses in Israel who was working down here, or even much lower in this chart. He was working at a factory at the Dead Sea where they produce these highly chlorinated, highly brominated type of compounds. And if we look at the chart, we see what we only show here are the contributions of the chlorine. And we know that in between the two peaks and at the high m/z end, we have additional isotope peaks because of carbon and other elements which might be there, as we have seen in this particular case. So that's what we see. And this is the information which we get. But you can use this chart to recognize chlorine and bromine contributions. Another very useful table is this one, basically telling you that from the relative abundance of the M+1 peak, you can predict the maximum number of carbons which can be present in this molecule. It can always be less due to other contributions, but it cannot be more. Yeah, and basically the M+1, if you divide by 1.1, you get the maximum number of carbons which can be there, but you have to be careful. The table also allows you to deal with the question I got just before the break, and to illustrate what is the immediate consequence of basically the statistics we are doing. So just assume that you have a compound with 90 carbons. 90 times 1.1 is 100, which means that for a compound of 90 carbons, the probability of having a compound with only carbon 12 and a compound with 1 carbon 13 is actually the same. And then the probability of having 2 carbon 13s or 3 carbon 13s or 4 carbon 13s is getting substantial as well. The immediate consequence of this is that if you have more than 90 carbons, the monoisotopic peak is no longer the most abundant peak in the spectrum. So you actually move to M+1 if you have 100 carbons, and if you would have 400 carbons, the most abundant peak in the spectrum will be the m+4. And the monoisotopic peak is only a minor peak in the spectrum. So if at any point you have more than 100 carbons and you look at the mass and you want to apply the nitrogen rule, you basically have to search for the monoisotopic peak, because the nitrogen rule refers to the monoisotopic peak and not to any of the other isotope peaks. Yeah. You should also be aware of the fact that the M here depends on what you do. So if you do electron ionization, M is M plus dot. And M plus 1 is M plus dot plus 1. If you do protonated molecules, positive ion electrospray, M is M plus H. M plus 1 is M plus H plus 1. If you do negative ion mode, you get the M minus H. You get M is M minus H. And M minus H plus 1. And M minus H plus 2. M plus sodium plus 1. With M plus ammonia and M plus potassium, you have to be aware of the fact that there will be contributions due to the ammonia and to the isotope pattern due to the ammonia and the potassium. So then it's getting more complicated, but we have software for that. Yeah. You should be aware of the fact, and I added this page because of the question I received, that there are some very rare situations where you see something weird in electrospray. So here you see two mass spectra from alpha carotene. And if you look at the structure and recall when do you see something in electrospray, you would say, I will not see this. But you actually do see this. And depending on the mobile phase composition, the spectra will be different. So these carotenoids are frequently analyzed using C30 stationary phases, and then you use mobile phases with low percentages of water. And the spectrum you get here is shown here. According to the nitrogen rule, the 537 would be the M plus H. The 536 would be the M plus dot. So in this particular case, according to the nitrogen rule, you get the M plus dot. If you use a mobile phase with a higher percentage of water, you will actually see that the M plus H is favored and the M plus dot is only a small peak. So you have a competition between these for this particular weird molecule. Yeah. And you can see that actually there's still some M plus H here because the peak is higher than what we would theoretically expect from the isotope pattern. This is something which we can see. But for larger molecules, make sure you look at the monoisotopic peak, and I will show you an example of that shortly. I was referring to the mass defect difference, so the M over Z difference between various forms and various isotopes which we use. And this is something which we can actually see by using a high resolution mass spectrometry. And here we have the simulated, so the calculated isotopic pattern for a unknown constituent from an onion bulb. And we zoom in here and get the simulated isotopic pattern, which we get. So we can actually, because we have high resolution at 400,000 in this particular case, we can discriminate between the 13C2, the 018, and the 34 sulfur isotope peaks in the spectrum. And then you say, well, in simulation, you can do everything. So let's get it for real. And here we have M plus 1, M plus 2, theoretical, and measured. And you see there are some a relative abundance difference between the real and the calculated one. But most of you are aware of the complexity of a sample when you have an extract from an onion bulb which you analyze, because LC is not as good as we think. We have some peaks running under it, which will disturb the story. But still, we can use this type of information to get along. Is the question answered from the previous?
Yes, thank you.
Okay, okay. And I will show you an additional example shortly. So let's proceed and let's come back to the MS spectrum of the bradykinin. And since I have the amino acid sequence, I also have the elemental composition of the compound. And based on the elemental composition of the compounds, I can use software to predict the isotope pattern of the M+H. And it looks like this. And if we have this, we can simply say, okay, let's now predict the isotope patterns of the doubly charged ion and the triply charged ion. So what we do is we take these three peaks, we add 1 and divide by 2. And we get the isotope pattern of the doubly charged ion. And if we add 2 and divide by 3, we get the isotope pattern of the triply charged ion. And if you have a look at, again, these simulated isotope patterns, you can immediately see that the distance between the isotope peaks in the spectrum is 1 divided by the charge. So we have 1 unit here, we have half a unit here, we have 1/3 of a unit here, we have 1/4 of a unit here. Yeah. Of course, you need high resolution mass spectrometry to resolve the isotopic patterns of the doubly and the triply charged ion. Because if you would simply use a quadrupole, you get pictures like the ones in the inserts. Yeah. This is a singly charged ion with a nice difference of 1 unit between the various isotope peaks. And if at the same settings we get the zoom in of the 530, we get this hump. But the quadrupole, and we use the quadrupole for this, is giving us unit mass resolution, so it cannot resolve the isotope peaks which you see here. So you get this hump. And you should be aware of the fact that the problem with the with resolution in the quadrupole is always at the high end of the spectrum. And at the high end of the spectrum, it's working properly. So the instrument is not broken or something like that. There's not a failure of the instrument. Basically, this indicates I must have a multiply charged ion. And I can deal with that and then calculate what is that, or go to a high resolution instrument to see what is actually going on. Okay, let's push this further. Let's push this to an extreme. Let's take a small protein. In this particular case, we have lysozyme, which is a protein with 40,300 something mass. And what we look at here are the spectra which we get if we zoom in at M over Z 1431. And actually what we get, and we get it at different resolutions because we use different scan times at the Fourier transform ion cyclotron resonance mass spectrometer, which was used to acquire these data. And if we look at the spectrum at a 100,000 resolution, between the red lines, which actually span 1 mass unit, we actually see 10 peaks, indicating that this must be the M plus 10H 10 plus. It must be a 10 plus ion. The monoisotopic peak of this particular compound is probably sitting here or even hidden in the noise. So if you would just say this and I multiply by 10 and use the nitrogen rule, you don't get a good value. You have to go to the monoisotopic mass. And that's the difficulty which you have if you have large molecules. So for large molecules, the nitrogen rule is getting complicated because you have to think too much, I would say. Finally, also with small molecules, you can see multiply charged ions. Like in this particular case, we have a compound with even less than 500, and it's giving us a doubly charged ion. And I've zoomed in on the isotope patterns to you can actually see what we have. So we have 1 unit here, we have half a unit between the isotope peaks here. And if you look at all these numbers, you can actually see the separation of the various isotopomers because we have some chlorine present, which creates these type of things. And that's what we can see. But in general, you would look at the picture as a general and simply use the values which are there. Any questions on the isotopes? So is everything clear? Then we will simply have our second break right now before we move to the last session. This went a bit fast, but I was expecting to get a little bit more questions. Yeah, especially since we are with 80. So I see you in 10 minutes. I'll walk around.
See you in 10 minutes, everybody. Please continue.
Okay. So as you can see, we are running a bit fast today, but it's always a bit difficult for me to predict how many questions there will be. And some sessions will be more tough than others. And especially sessions where we have discussion of exercises, it's always extremely difficult for me to predict how long it will take. Okay, in the last session, we will basically look at high resolution mass spectrometry to get an idea of what's going on and to look into calculating elemental composition from accurate M/Z values. And there are a number of issues which have to be discussed. First of all, you should be aware of the fact that there are basically 4 important parameters by which you can compare mass analyzers. And these 3 of these 4 are given in this table. The 4th one is not relevant at all in the current setting, but it's of course very relevant because that's the price, the cost. Yeah, these are very relevant. And the high resolution mass spectrometers are always more expensive than the unit mass resolution instruments. So basically the 3 important parameters are resolution, which means mass spectrometric resolution, not chromatographic resolution. And with almost all instruments, the resolution has been defined as being the ratio of the M/Z value and the full width half maximum of the peak at this M/Z value. So if an instrument manufacturer says, I can sell you an instrument with 200,000 resolution, you should specify for which M/Z value this has been measured, because that makes a hell of a difference. Yeah. If you have a unit mass resolution instrument, it doesn't make sense to do this calculation because the numbers are not relevant. So this is something which you only do for high resolution instruments. The second important parameter is the mass accuracy, which basically is the difference between the measured and the calculated M/Z. And quite frequently, it is expressed as a relative error in ppm, calculated from measured minus calculated divided by calculated multiplied by 1 million. And that's a very correct way of expressing that. But especially for small molecules, I actually prefer to use the absolute error to basically see how much difference is. And I have there's a higher logic in using the ppm for that, which doesn't fit to my scheme of logic. I'm not a very logical person, I can say. And then finally, of course, we have a wrong term for the third parameter, and I called it sensitivity. But sensitivity officially by definition is the slope of the calibration curve, and that's not what we mean. It basically means how much sample do I need to get either a good full spectrum in MS or MSMS or MS to the power n, and how much mass I need, how much compound, what's the concentration I need to get good sensitivity, good peak, good signal to noise ratio in selected ion, so selected ion monitoring or selected reaction monitoring. These are important parameters. What is very important with all high resolution, with all mass spectrometers, is doing a proper calibration. And we have nice procedures for that, proprietary software procedures, where we basically acquire the mass spectrum of a calibration mixture, which we continuously infuse, and then the software performs the necessary calculations and saves a calibration table used in measurements. And this is a procedure which applies to all instruments. If you have a high resolution instruments, you have to do additional tools and additional things like doing internal or external calibration with the time of flight and orbit map instruments. And the reason for stressing calibration is that when I run this interpretation course within companies, I always say, send me some of your data, and I implement some of the data in the course, at least when I get useful data, because for a number of cases, I got data where calibration was really, really bad, and you can't do anything with it. So make sure you have your calibration done properly in your instruments. And then, of course, you can compare the different mass analyzers in terms of resolution, mass accuracy, and sensitivity, which is there. But when we say we have high resolution instruments, and this should be 60,000 by now, the time of flight instrument. If we say we have high resolution instruments, quite often we do not really understand what we have. So let's look at the spectrum. And what we do is we do infusion in positive ion electrospray of human urine using a 7 Tesla Fourier transform ion cyclotron resonance mass spectrometer from Bruker. And the spectrum that we get is given here at the top. We acquire a range between 100 and 600. Yeah. And if we actually blow up this spectrum by a factor of 10, we get the lower spectrum. And you can see that in this spectrum, we basically have compounds at every single mass. And there are people who believe that you can do quantitative analysis of compounds by infusing them in a high resolution instrument. If you also believe that this is a useful and good way of doing quantitative analysis, I urge you to read some papers on matrix effects and ionization suppression in LCMS, because no, you need separation. So what we can do, because we have high resolution instruments, we can zoom in the spectrum, and that's what we have done. So now we have a window of only 24 units wide, and you see some of the peaks have been annotated, and those of you who are working in metabolomics and so on and so forth and looking at plant metabolites are familiar with these type of procedures where peaks are annotated. But in fact, this is not showing high resolution mass spectrometry. This is showing unit mass resolution. So let's zoom in further. Let's zoom in over 1 mass unit, slightly more than 1 mass unit actually. And then we can see, for instance, for this particular compound, which is annotated to be hippuric acid, and we see the hippuric acid 13C isotope peak here at 203. So let's further zoom in on this part of the spectrum. So what we see is this. So next to the 13C isotope of the sodiated hippuric acid, we see that there's the sodiated molecule of glucose, which is showing a mass difference of about 2 millidalton. And that's high resolution mass spectrometry. The ability to discriminate peaks with a very small mass difference. So we can actually look at this and discriminate it from this one, which is only 2 millidalton away. And we see there are some other isobars present in the same very small window, because this is a window of only 10 millidalton wide. And that's what we are there. And that's the information which we take. If we have properly calibrated the instruments, we can take the value here and start doing calculations based on the accurate M/Z which we have got. And I've already explained all of this. I just wanted to point out that the mass defect in physics is differently defined from what we use in mass spectrometry, and that's indicated here. Okay, so if we do accurate M/Z determination, we can actually use that with software to do elemental composition calculation or molecular formula. And software tools are available, for instance, in your data processing software, and there can be very simple, straightforward tools with very little intelligence, and there can be more advanced tools. There's a lot of chemistry information in. And with respect to that, I should point out to you the so-called 7 golden rules set about by Keen and Veen in some years ago, where they basically put in a lot of chemistry background in doing the calculations and developed software tools in order to do these type of calculations. And basically said, if you work on natural products, you can basically, if you have a mass up to 500, this is the typical number of carbons, hydrogens, nitrogens, and so on, which you have to consider. And of course, when it comes to sulfur, chlorine, bromine, and silicon, you can actually decide from the isotope pattern whether these elements are present, because they show this distinct isotope pattern, which is typical for sulfur, for chlorine, for bromine, as we have discussed. So we can do elemental composition calculation. And sometimes people say, well, we can do elemental composition calculation, so we identify unknowns. And I say, no, we don't identify unknowns by just elemental composition, because one elemental composition can actually correspond to numerous isomeric structures. And this is something which we can see if we take an elemental composition and search them into a compound database. And I will show you an example of that shortly. And some important compound databases which are around are, for instance, the PubChem or the GemSpider database, which contain up to 90 million compounds. Yeah, and these are general databases. Perhaps for certain applications, you would prefer to use a more specific database like the human metabolite database or the methylene database or something like that. Yeah. So let's look into some examples. So the number of hits you get in doing the elemental composition calculation depends on the software which you use. It depends on the M/Z value you do the calculations. So in general, if you have a higher M/Z, you get more hits. It depends on the number of elements which have to be considered, and I will show you an example of that shortly. And it depends on the accuracy at which you have measured the M/Z value. So let's do calculations for different M/Z values calculated for basically a compound which I know is only containing carbon, hydrogen, nitrogen, and oxygen. And the calculations were done with this search window, and I was looking for protonated molecules, so I only looked at even electron ions. And if I get the data for this compound with a quadrupole, I get 71 hits. Doesn't work. If I use time of flight of Orbitrap, I get a small number of hits. But still, if you get only one hit, you cannot state that you have identified the compound. Because for the elemental composition of C20, H21, N3O, which is the molecule instead of the protonated molecule, the GemSpider database shows me more than 2,000 structures. And if you state, I have identified the compound, if I have to still to choose between 200,000 compounds, when you think that is identification, we have a disagreement of opinion, because I need a structure. And perhaps you would say, I would not only need to have the structure, but also the enantiomeric issues which are there, the chiral issues which are there, to really identify the compound. And for somebody like Sophia working in pharmaceutical industry, that will be an important issue. I stated the number of elements to be considered is also important. So if I would do the same calculations if I done here, and then added the possibility that there is one sulfur and up to 3 fluorines in, I get actually about 4 times more hits. So all the numbers are multiplied by 4 in doing this calculation. So if you can rule this out, exclude that, that actually helps. And this is something which is basically on the basis of the very difficult story on the next page. So what they actually decided to do is we want to do, we will want to search the PubChem database with metabolomics data. So instead of using the complete PubChem database containing 90 million compounds, they actually created a subset by stating we only have to consider compounds where we have carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphor, because that's what we see in natural compounds. And then the database reduces to a size with only 3 million compounds. Well, only 3 million. Yeah. So what we do is we actually perform calculations and search database for a number of masses. And basically what we do is we take a 10 plus or minus 10 ppm bin around this mass and see which elemental compositions show up. And we had an idea what the compound was, but what elemental compositions show up in this 10 ppm bin around the mass which is given. And you see that for the phenylalanine, which is the first, we basically have 2 elemental composition. There are 86 structures for the actual elemental composition which is there, and only 5 for the others. And you see similar numbers as well. So being able to state that the elemental composition is actually this and not this is already helpful in reducing the number of hits, but still you have a lot of structures to consider. So you have to do a lot of thinking in order to do this, to get this right. And you see that depending on the mass, you get a lot of things there. And perhaps you say, well, it's a bit weird that for the high mass compound, we get so little hits, but at a certain stage, the compounds are not simply there in the database. So that's something which is there. So let's look at a very simple and very poor piece of software which is there. I get a message from Ilana on chat, which unfortunately I cannot read because I'm not capable of reading this language. But perhaps God will be able to show us later. So let's do some calculation. And what I decided to do is I will do the calculation for the M over Z 101. And I have a large window because I was doing the work with a quadrupole in this particular case. And I get a whole range of hits. And one of the important tools in sorting out what is going on is the second column in this table, which is the RDBE. And I will introduce the RDBE in detail in our next session on Wednesday. But for the time being, it's important for you to know that if you would expect an M plus H, the RDBE should have a value ending at 0.5. And if you have an integer value, you have an odd electron ion. So from the 22 hits I get for the M over Z 101, I can actually remove all these by the red line because they have an RDBE of which is an integer value. Yeah. And in the same way, I can look at some things. And one of the solution for the 101 is C3H04, which is not a useful molecule. It will not exist. So I can remove these from the list as well. Yeah, and that's due to the fact that this software is not very intelligent. You should have a more intelligent software. And in most cases, you have them available in your instruments, or the software of your instruments, I should say. So let's pick out one of these elemental compositions and then search the database. So I take one of the elemental compositions, I remove the H+, I get the C5OH, and I get a whole range of different structures. So the thing which you now need to do is get the MSMS data of your unknown and see whether from the MSMS data you can exclude a number of these possibilities. And later on in the course, I will actually give you some examples where we do this and where we exclude and do this. In this particular case, I didn't do that, but it's a possibility which you can do. So if we would apply this same procedure to what we have in our resolution mass spec data from the human urine, so to basically the hippuric acid, and we take the protonated version rather than the sodiated version, but that doesn't really matter. I will search this, and I search the RemSpider database with this, and I get a huge numbers of hits. And that means I can have all kinds of structures. If on the other hand, I say, well, I conclude that the elemental composition actually should be that one of hippuric acid, so it should be this one, I only get 16 hits at the highest accuracy, highest resolution level, and that's what I'm working with. So that's what we get. So let's look into what we actually get. 16 is still a lot. So basically what I decided to do, I'm looking at human urine. Let's change database. Let's use the human metabolite database, which is around there as well, and search the ion of this. And depending on the mass accuracy I invoke, I get a number of hits. So we use an FTICR, so we can work with this. So we get only 6 hits. And all 6 hits have the same formula. And the 6 formulas are shown here. And now you are doubting my abilities because I say I show you 6 structures and you count only 5. That's due to the fact that in the database there is a hippuric acid and the N-benzoyl glycinate, which is both this structure. So they are in the database twice, while in fact it's the same structure. And that's what is important for us. So what we now need to do is we need to get MSMS data from this M over Z 180 and see whether we can decide which of the compounds is actually there. So perhaps you would say, confirm whether you actually have the hippuric acid which has been claimed. Yeah, so this is a procedure which we do, and I will show you examples of that later on. We looked at mass defects, and we said, well, mass defects have distinct values and so on and so forth, and it's perhaps a useful way of looking at mass defects in this way. So you can see there are some elements which have a huge mass defect. There are some elements which have hardly any mass defect. And that's important. In basically what I'm trying to do is I'm trying to build with you some feeling what is actually the issue with mass defect. And to introduce you to the idea of using isotopes. Well, if you perform elemental composition calculations from just the accurate M/Z, in my opinion, you're actually throwing away information. And that is the information which is in the isotope pattern. So at some point, I was very glad that Bruker, being the first, and other instrument manufacturers following, developed a software where they actually used not only the accurate M/Z, but also the accurate measured isotope pattern. And using a time-of-flight instrument, you are capable of getting a reasonable accurate isotope pattern as long as your separation is sufficient. So in this software, what they actually do is they perform the conventional elemental composition calculations. And this is an intelligent software which filters by chemical rules, so the number of hits is not too high. And from the resulting hits they got, they actually predict, using software, the isotope patterns. And then they compare the isotope patterns, so the predicted ones, calculated ones, with the experimental. And the correlation they got between the calculation and the experimental values, they express in a so-called sigma fit value. And then they get the hits, and they do not sort the hits according to mass difference, the M/Z difference, so the mass accuracy of that, but actually sort them according to the sigma fit values. So they basically indicate that if the elemental composition and the isotopic pattern nicely fit together, there's a larger probability that this particular hit is actually the correct elemental composition. And that's what they do. And this is a very intelligent way of using this software. And other people like Orbitrap users sometimes actually take advantage of the fact that they see these 15N or sulfur isotopes in their spectra and know that the sulfur must be there, so you can filter out any other possibilities. Any questions? If not, I'm extremely happy because I have been completely clear and you understand anything I told you. So it will not take you much time in the afternoon to work on the exercises because you understand everything. So it's all very easy. So let me introduce the exercises.
Sorry, can you expand a little bit on the relative mass defect, or will you do it in the other session?
So what do you mean?
You talked about the relative mass defect.
You mean in this page?
Yes. Do you plan to expand on it in another session, or is it?
I'm not planning to do that. No.
So how can we use this relative mass defect? Can you maybe tell us? Like,
I would say I would like to refer to the paper from Turban and Ferrer. They explain a little bit, but it will go too far to do that in this course.
But okay, thanks for this advice. But maybe just in one phrase, in what way can it be useful? Maybe just for elemental composition.
Again, to get more certainty on elemental composition.
Okay, thanks.
Yeah. So after each session, there will be exercises, and the exercises are vital and extremely important in the course. I once was approached by a pharma company, and they said, "Can you run the MSMS interpretation course with us? But doing all these exercises takes too much time, so leave out the exercises." And then I said to them, "Under these conditions, I will not come. Sorry." So the exercises are vital. I think it should be possible to do the exercises in about an hour. And hopefully you will succeed in that. And please divide your time over the various exercises. I've been running exams for students, and sometimes they spend all the time during the exam just looking at one exercise. I don't understand that. And they don't get any points, because if they would have moved to the other exercise, they might have got better results. Our next session will start with an interactive discussion of the exercises. And after each of the next sessions, you will actually receive from me or from GAT, because that's the way we organized it, by email, a handout of the works exercises, and sometimes some additional pages which I showed during these sessions. So that's everything I need to tell you. There are some exercises there, and you can play with them. And if you don't have any further questions, we'll stop for today. And I see you all on Wednesday. Tomorrow I will be running the course somewhere else, a different one actually. Yeah. And I actually have a live setting in a large room, a very large room, where they can fit in 100 people, and there will be only 12. Okay.
That sounds safe.
Yeah. I hope so, yes. See you all tomorrow, and have fun in the exercises.
Not tomorrow,
not
Wednesday.
Tomorrow, on Wednesday. See you all on Wednesday, and have fun with the exercises. Bye.
Thank you very much for now. And of course, I'll send you the recording link once it's available. Thank you very much for today. Have a good one.
Bye.